Hi. um, I'm presenting with Lucas.
Okay,
Lucas, are
perfect.
you there? Yeah, okay, cool.
You and would you like to introduce also the whole team? I know I see several authors, so please introduce them. Thank you.
Right.
Thanks.
Hi, my name is Lucas Herman, and I'm an undergraduate researcher at Carnegie Mellon University's Data Interaction Group.
Hi, I'm Kania, and I'm also an undergrad at Carnegie Mellon University. For this project, they're not here, but we worked with Travia, Nur, and Dominic, and Scott is here. And I guess we'll get started.
Yeah, so today we're going to introduce you to PIXLISE-C. Pixel helps examine the structure and chemistry of biosignatures. The fine-grained structure can help determine fossilized laminations that could have been deposited by ancient microbes. This is stromatolite. The unique chemical makeup of this rock indicates early life on Earth. The Pixel tool, which we will talk about next, is designed to isolate the chemistry in a sample like this one. In order to talk about PIXLISE-C, we must first introduce Pixel and PIXLISE. Pixel is an astrobiology tool, a tool for researching life in the cosmos that serves as part of the Perseverance rover. The Pixel sensor is used to gather small-scale information about the chemical composition of rocks, which aids in the process of understanding the geological history of Mars. Pixel captures raster maps of 15,000 spatially localized spectra. Each spectra has peaks, and each peak is roughly proportional to the abundance of that element. Here's an example of one of the grids of capture. Once data is collected via Pixel, it is brought into PIXLISE, an interface that allows for further analysis. Researchers select points via the context image and are able to view relationships of chemicals in a given sample set. Through the spectrum, researchers can label peaks that serve as signatures for various periodic elements. Given the workflow that organizes and quantifies elements, my team decided to create a tool for comparing the elemental data after it had been labeled through this process. In other words, how might we overcome some of the pain points in grouping and comparison of periodic elemental data? Our research began by need-finding interviews with Scott Davidoff of the PIXLISE team. Then we moved on to ideation along with a user interview of Dr. David Flannery of the PIXLISE team. Finally, we implemented the prototype that would become PIXLISE-C. Connie will walk through more of the PIXLISE-C use case.
So this is the prototype that we created, and I'll walk you through an example use case. So say I'm an astrobiologist and I want to look at this sample and identify minerals. I'm using a data set called King's Court, which uses real pixel data. So on the top left, we see an image, and overlaid on top is a grid representing where the pixel tool took samples from. We haven't grouped any of the points yet, so the comparison sandbox on the top right just shows a bar chart representing the average of the data. Each data point in the grid will contain data about the chemical elements that are present at that location. So the x-axis of both the bar chart and the parallel coordinates plot are composed of elements of the periodic table. The y-axis then represents the percentage of the sample that the elements make up. So I'm going to start off by running a k-means clustering algorithm with PCA dimensionality reduction to automatically create groups for all of the points in this grid. After the clusters are made, the interface updates to show me the individual bar charts for each group. Since my goal is to identify minerals within the given set of points, I first need to cluster the points into groups and then use my own knowledge of chemistry to identify what mineral each group might represent based on their elemental composition. Now that we have these groups, I can look at the parallel coordinate plot on the bottom right to get a quick understanding of how the groups compare to each other. I see they all have distinctive element makeups. For example, it appears that the teal group has much more vanadium and arsenic than the other ones. Maybe after an initial review, I feel pretty confident about the blue group. I can annotate it and I can also lock it. Now, if I switch viewing modes in the context image window, I can view the individual points and see how they compare to each group in the comparison sandbox. It will also bring up the annotation for that points group. Maybe after reviewing the individual points bordering the blue circle area, I feel like the clustering was inaccurate. I can manually change the points with the paint tool. Since I locked the blue points earlier, they don't change even though some of them intersect with the paint area. To further review and confirm my groups, I can play around with the filtering and sorting settings in the sandbox in order to compare them against each other and to make sure there isn't too much variation within the groups. Too much variance in a group might mean that I don't have the correct number of clusters to begin with. I can switch between log and linear scale, remove elements on the x-axis that aren't relevant to my analysis, sort the x-axis by mean variance and coefficient of variation. Finally, if I want more granular information about an element within a cluster, I can hover over that bar to see more important statistics.
The following links are helpful for further information on these topics. Thank you for your time. Feel free to contact me at the information below. Special thanks to Dominic Morris for advising us and Scott Davidoff for taking the time to work with us.